Hi, I'm Ed Marszal, President of Kenexis, and I'd like to welcome you to this encore performance of risk analysis of wired versus wireless transmission of process measurements. This is an encore presentation of a presentation that was originally given during the October 2014 Emerson Global's Users Exchange. The developers of this presentation included Gary Hawkins of Emerson Process Management and also myself, Ed Marszal, the president of Kenexis. Okay, first off, in this presentation, the key to it is that we'd like to discuss whether or not wireless transmission is as good as wired transmission. Right now in industry, there's a lot of fear and a lot of just dismissal of using wireless communications as being fallible, unsafe, and unreliable without a lot of real analysis of the different types of transmission modes, what failures they're susceptible to, and what you can do to work around the limitations of the different wiring schemes. So we're going to present a method for analyzing for your particular installation what is good and what is not, and how to do that analysis assessment. A lot of people believe that wireless transmission is not as reliable as wired transmission, and that may not necessarily be true depending on the specific installation. A lot of people are certain that wireless is not suitable for critical services and specifically safety services, and that also is not necessarily true, especially for safety instrumented systems. If you look at the IEC 61511 and 61508 standards, they really don't do anything to exclude wireless mechanisms. So what you need to do is you need to assess those systems to make sure that they do meet the requirements for the SIL levels that you're trying to achieve for safety critical systems. And then we're also going to want to look at, well, what can go wrong in the different types of systems and what can we do about it. So what this presentation is geared to do is to compare and contrast wired transmission versus wireless transmission using tools of risk analysis to get an unbiased and objective assessment, as opposed to just using rules of thumb and the common thinking that's available today. And we'll start with a little bit of a background on risk analysis tools. So there are tools that are entirely qualitative and there are tools that are semi-quantitative. Like layer of protection analysis is a semi-quantitative approach. It looks at order of magnitude jumps in risk, and it really has a limited set of different logical types that are available. And I'm sure many of you are familiar with probability and severity matrices, as these tools have been used for dozens of years, tens of years, for tasks ranging from reliability-centered maintenance to risk-based inspection to hazard and operability studies. They just give coarse general descriptions of the risk. Now, beyond qualitative analysis is quantitative analysis, where you try to actually calculate probabilities and frequencies and calculate the consequences of loss of containment events. And a tool to perform this type of assessment would be a fault tree analysis, or even a simplified fault tree analysis, which gives you a little bit more flexibility in the accuracy or the precision of the numbers that you're using and the different types of logical constructs that are available to you. Now, the outcomes that when you perform an analysis, outcomes can vary from site to site. This is not only possible, it's to be expected, because different sites have different equipment configurations, different maintenance programs, different stressors, and different situations that occur on one site that might not occur in another, that can add new failure modes and also change the rates at which different failures are likely to occur. Okay, and the quantitative analysis of risk is what we've chosen for this discussion, basically to set the problem up and create a starting point for you to perform more detailed analysis of your facility to determine if wireless may be appropriate for some situations in your plant. Okay, I'm going to start by giving a general description of fault tree analysis and how fault tree analysis works. Fault tree analysis begins with basic events. They are the root causes of things that occur in unwanted accidents that we're trying to calculate the frequency or the probability of. So basic events are an event that's so basic that you don't want to break it down further and you simply want to attempt to quantify it. And you'll quantify the basic events as either probabilities or frequencies, and you can perform that assignment based on statistical analysis or by using reliability engineering equations to calculate probabilities. From there, the basic events are related to each other with logical relations, either AND gates or OR gates. And mathematically speaking, the logical relation can be mathematically modeled using probability math. So if I could slightly oversimplify the problem, in an OR gate, what you're going to want to do is you're going to want to add the probabilities together. And for an AND gate, you're going to want to multiply the probabilities together. And you continue to take that approach all the way up the tree until you find the top event, and that is the failure or the event of interest that you would like to quantify. Now, before I go into the fault trees, let me talk a little bit more about safety nomenclature, because what we're going to be looking at in the fault trees that we're going to see in the next few slides are revealed or overt failures. They're failures that announce themselves and that you know about them almost immediately. And for transmission, wired or wireless transmission, we're going to find out that almost all the failures that we're going to be concerned with are revealed or overt failures, because they're going to announce themselves in a loss of communication that is going to probably cause your plant to go to a safe or a shutdown state. As I mentioned, these types of failures are generally safe. They'll place a plant in a trip condition, but you put the plant in the trip condition unnecessarily. Sometimes these are also called spurious trips or nuisance trips. Sometimes these failures are dangerous because sometimes when you shut down a plant, you can create a new hazard that you didn't expect. And nevertheless, starting and stopping plants is a hazardous condition of its own that we would like to avoid if at all possible. Now, the other type of failure are the unrevealed or covert failures. They don't announce themselves. They lie in waiting until a demand is placed on the system and it cannot respond. So for a safety instrumented system, if the contacts on a relay are welded shut, you don't know that those contacts are welded shut until you try to open the circuit and it doesn't open. And in this case, it's generally dangerous, especially for safety instrumented systems, because the safety instrumented system cannot respond to the hazardous condition. And you need to make sure that those types of failures all allow you to achieve a tolerable level of risk. Now, as I mentioned previously, we're going to be primarily concerned with revealed or overt failures because failures in communication systems are generally overt. So if you have a wired system, especially if you're doing a de-energized to trip safety system, what that means is anytime you drop a wire or open a circuit, that's going to de-energize the final element of your safety instrumented function, causing the plant to go to a safe state. Well, the same is actually quite true of a wireless system, because with wireless systems, the safety, if you will, is not in the medium by which the signal is sent, it's in the protocol for sending and receiving that signal. So there's logic on the sending end that's packaging up packets to be sent to the receiver, and there's intelligence on the receiver end to make sure that the data it's received is timely and valid. And if the data received by a final element or any receiving device is not timely and is not valid, it is very easy to detect and then cause the system to respond in such a way that it moves to a safe state. So let's first take a look at fault tree analysis of a wired system. Some of the typical initiating events for wired systems would be wire breaks. So either the wire breaks itself or is cut, or even in some cases the connection to the wire could be dropped. There are also partial circuit failures, which is kind of a wrong measurement as opposed to a loss of measurement. This is going to be the result of loose or corroded screw terminals or ground faults that are partially dragging down a circuit. So for an analog circuit, you might have a 4 to 20 signal that, because of some sort of impedance on the circuit, the transmitter might be trying to send 20 milliamps, but as a result of excessive impedance, you might only get 16 or 18 milliamps at the receiver. That's what we're going to consider a partial circuit failure. So taking a look at a typical fault tree of a wired system, you'd see that the top event is loss of communication, and that can happen if either I get a open circuit or a loop failure. And I further broke open circuit failures down into wires either failing or being cut or terminals being dropped. And the numbers that I'm showing you here again are for illustration purposes only. They're not meant to apply to all sites. I did use data from published databases, databases from Cisco for wireless communication equipment, NPRD, National or Non-Electronic Parts Reliability Database, the 1995 version for some of these components is where I grabbed the data. But data for a terminal drop, a wire falling off of a screw terminal, I have refineries that have told me that they have never experienced a drop wire in their history. I have other refineries that tell me that they usually experience one per day as a result of vibration or some other anomalies. So these numbers are going to really vary from site to site, and you need to think about your particular facility when you're doing this type of analysis. So you put in the failure rate per device. Let me back up a second. So you put in the failure rate per device multiplied by the number of devices to get a total frequency. So even though the frequency of failure of a wire segment might be 3 times 10 to the minus 4 or 3.5 chances per 10,000 years, you're going to have a lot of those segments. So think about wiring of a transmitter. You've got your wire from the transmitter to the local junction box. From the local junction box, you might have another intermediate junction box in the field. From your field, you're going to get the home run cable into the marshalling terminal. From the marshalling panel over to the PLC panel, and from the PLC panel up to the device itself. You're going to have 4, 5, maybe 6 different wires in the circuit for an individual device. So the numbers that we have here, the quantity of 100, is going to be 25 devices times 4 segments per device. So we take all those numbers for wire failures and terminal drops, and then we also take similar numbers for corroded terminals and ground faults in the loop failure. And then when we add everything together, we expect at least one of the loops in a wired system that has roughly 25 instruments or a typical process plant. You're going to expect at least one communication failure at least every 2 years. So that's where the MTTF is mean time to fail, and we calculated a number of 2 years for that. So now let's go on to wireless transmission. Again, the initiating events for wireless transmission are going to include other things that you don't have on the wired system, like a battery failure. You're also going to have things like local interference, and this is one of those things that's going to be extremely hard to quantify. and it's going to vary from facility to facility, depending on what the electromagnetic interference sources of your particular site are. Whereas we have experience with very frequent communication failures, and we also have some facilities that are remote that have gone years without getting even one scan, one cycle of wireless communication dropped. And the one thing that you're going to need to remember when you're doing your wireless system design is that even though you might get intermittent interference through something like a lightning strike, that interference is very short-lived, and if you have a larger process safety time or an allowance to miss a few scans on a control loop, if you can drop a few scans and continue to operate, then you won't necessarily need to send your plant to a safe state and cause a shutdown. You can kind of hold the last value for a few scans until you actually confirm that communications have been dropped. Now, with a wireless system, the partial circuit failure really doesn't exist. With wireless, any type of digital communication, you're either going to get a good communication or you're going to get junk. You're not going to get anything that's slightly degraded. It's either good or it's not. So we really don't need to worry about those partial circuit failures. Okay, so looking at the fault tree analysis for the wireless transmission, again, with 25 field instruments, each one of those field instruments is going to have a radio built into it that is performing the wireless communication. And that's on the instrument side. And then you also have the receiver side that includes radio failure of the receiver, failure of network interface cards, failure of network cabling, because there is still going to be some cabling, it's just not going to be from field instruments into the control room. And there's also possibilities for your communications interface device to fail, the one that's connected to your PLC that's going to bring the data in for processing. So doing this simple analysis, we've calculated for that same 25 device system a mean time to failure of 4 years. So just doing a very quick analysis, you can see that the failure rates from a cold eye quantitative analysis are in the same order of magnitude between wireless and wired systems. So that's something that you're going to want to consider. Now, looking at this is a great tool to have both of these fault trees available, because then you can start bringing other things into the assessment. So one of the things that you'll see is missing from this fault tree is the frequency at which background noise, background electromagnetic disturbances cause the communications to fail. And that's something that's really so site specific that we didn't want to put it in here and try to quantify it. But it is a valid and realistic concern that when you're doing this for a process plant, you're going to want to consider. The other thing that we didn't include here on the beneficial side is redundancy. We're just talking about devices in the field communicating to one receiver. Well, there is a possibility for redundancy in wireless systems. You can have a mesh of multiple receiving devices that work similarly to a handheld cell phone. As you're moving around, you might lose your signal to one cell phone tower, but pick it up on a different cell phone tower and never lose never drop your phone call. The same type of thing is available in wireless systems, and you can model it inside a fault tree analysis, even though we haven't modeled it in this illustrative example here. So now that I've given you the background on how to perform the risk analysis, how to mathematically analyze the differences between wired and wireless systems, let me give you a few thought-provoking cases where you might want to actually think a little bit harder about wireless systems and the concept that maybe you might want to incorporate them a little bit more into your work processes. Okay, so for the first one, there was a refiner that had a fire at a charge pump in a crude unit, and that fire caused damages to the cable tray in a neighboring hydroprocessing unit, causing that unit to shut down. Well, they were faced with a variety of options, none of which that they liked. The refinery was in a remote location. They didn't have access to sufficient cabling to be able to perform that repair for months. So in this case, the operating company considered using wireless transmission for some of the less critical indication-only measurements to allow them to reduce downtime. So what wire they had, they used to wire up speed critical control loops, and then they used brought the rest of the communications in using wireless in order to save them days and weeks of downtime. Okay, and in this case, the process throughput was about 30,000 barrels a day at $5 a barrel. Every day that they were able to get that process unit up running sooner saved them $150,000. Okay, another case is pushing the envelope on tank overfill protection. Now currently, API has a recommended practice 2350 for automated storage tank overfill protection, and that recommended practice, the key there is recommended practice, does not recommend using wireless for an initiating action that's going to prevent an overfill. So if you're measuring tank level and using that level to actually close a valve, the RP doesn't recommend that you use wireless. Of course, it doesn't recommend that you don't use wireless, but it doesn't recommend that you do use wireless. But in either case, you still have a lot of remote storage tanks where your overfills or the levels only trigger alarms indicating that some sort of action needs to be taken. Now, why did they do this? Well, basically because there's insufficient experience in the reliability of wireless devices. As we get more experience with wireless devices, this conservative position might change. Again, very similar approach taken for the first safety system standards, not using wireless buses. But something to think about, especially in tank farm solutions for oil and gas facilities and refining facilities, these devices are in remote locations, and wiring costs are going to be many multiples of the cost of the device itself. So in alarm-only situations and situations where, well, I don't have funding to actually put in my SIS, perhaps you might want to consider the lower installed cost solution of a wireless signal. And another benefit or consideration in using wireless signals for tank overfill protection is that you usually have quite a long process safety time. Your process safety time between when the alarm is supposed to come in and when the tank overfills could be 30 minutes to an hour to over an hour. So if you lose communication for 1, 2, 3, 4, 5 minutes, it's still within the process safety time and it might not require triggering a shutdown, again, improving the overall availability of your process plant. You really need to consider the costs and the benefits of a wireless solution. It might be the right solution for your facility. Okay, and when you're doing that cost-benefit analysis, you need to consider, well, what is the consequence of an overfill? What is the probability that a wireless system will fail to prevent that overfill? And use that in your thought process when you're determining which solution is most appropriate. Critical measurements. A refinery in Asia in the aftermath of a flood was trying to get itself back on stream. And what they noticed is that all of the devices that were wired were flooded out and shorted and needed to be either repaired or replaced, whereas all of the wireless communications was still in operation. They were able to survive the flood event, whereas the wired systems had a lower degree of survivability. This led that refiner to standardize on using wireless transmission for critical measurements because it could survive some of the events that the wired systems could not. So it provided a little bit of diversity. On that same note, looking at survivability, think about fire and gas systems, especially a fire and gas system that is designed to energize to trip. So you're going to want to open a deluge valve or turn on a fire water pump. These systems are usually designed so that you'll energize an output to cause that action to happen. Well, some process plant equipment needs to be designed to survive foreseeable accidents. And an excellent example of that are fire and gas systems where you're activating fire suppression equipment out in the field. And as I noted, these systems often are energized to trip. So even if I have excellent redundant wired communications, a single explosion can sever both of those wires depending on how the wires are run. Even if they're wired in diverse routes, a significant fire or explosion can cause both of those redundant routes to be compromised at the same time. In these cases, wireless systems are going to provide you a redundant route that has better survivability and is able to survive different impacts than wired systems. So if you, instead of going with two wired signals, had one wired and one wireless, you're going to provide an improvement on the overall survivability of your system. So business results achieved in these thought-provoking cases. Number one, the incident mitigation. It provided you quicker recovery of operations after a fire that damaged cables. In case two, for storage tank overfill protection, wireless may reduce your risk because it might be the only feasible, affordable solution in a number of cases. Case three, for critical measurements, it provided a paradigm shift to the operations company that said, if I have diversity in my communication types, I can improve the survivability of my system to major accidents that I might not be able to predict. Overall, all of these systems allow you to resume operations quicker after an incident occurs and also improve safety sooner. So in summary, you've seen, we've demonstrated that risk analysis tools can be applied to a wide variety of events besides just studying safety instrumented systems. They can look at the overall reliability and availability of different plants for different failure modes. Wireless transmission is going to offer you a savings in capital costs because you don't have to worry about the wire itself or the labor in performing the wiring. And it also shortens the time to implement, which again is going to be another time savings. The analysis of the causes of communications failures can help reduce the mystery of wireless. Right now, we're seeing a lot of knee-jerk reactions, a lot of people saying wireless is bad, and that's all driven from early adopter consumer wireless technologies that they've seen fail. Industrial wireless technologies are different. They're getting more and more proven, more and more robust, and the configurations with wireless meshes and redundancy are allowing improvements that are going to quickly allow wireless communications to surpass wired communications in terms of availability and reliability. Often when you're faced with hard choices, it's difficult to make a decision, and when you face those decisions that are tough to make, you really need to think about using quantitative analysis to help you support your decision-making process to allow you to make a more rational and defensible decision. If you want more information on the topics that we've presented today, this presentation itself, again, was just intended to be thought-provoking and help you push the envelope of what you are applying. And, things that we would like to hear from you are, what are your experiences with pushing the envelope and using wireless systems? Coming out of the conference, I was present in a number of sessions where they were using wireless communications, and the communications were flawless, even in non-redundant situations. So it's something to consider. And we definitely welcome your feedback. You can contact the authors directly, or also you might want to go to the Emerson Exchange 365 blog at the URL shown on the slide to discuss this a little bit more. It's a moderated forum that allows you to ask questions and get answers back. Thank you for listening to this encore presentation.